Welcome to ELE 201, Information Signals. As the class began, we were listening to some music. The Hotel California, one of my favorites. Sound recording technology has gone a long way since the phonograph first recorded sound. What we'll do first is open up the sound file for Hotel California in some music editing software. That way we can see exactly what signal, what data we're working with. So now I'm going to pull open some open source software, Audacity. Now, sound is just fluctuating pressure waves in the air. What we see here is the sound that's been captured by the microphone as a graph over time of these fluctuating pressure waves. We can listen to it.
Watch the sound. Okay. You heard it before, so.
So as you see, this is really just a graph of the fluctuating waves in the air. Now, several of you have probably played with this before. For those who haven't, let me show you. You can zoom in so you can see the finer details of the sound. At this view, it's not very informative. But if we zoom in, then we can see the beat and the intricate details. We can keep zooming
like that. Sometimes zoom back out. I'm going to need one of you who's this before.
Now, if we zoom in far enough, we'll see that, in fact, this is a sequence of individual numbers, these dots here that we see. Because this is a digital recording, it's actually a sequence of numbers, and the graph just tries to interpolate between to show us what the sound actually would have been between the samples. Now we can actually redraw. We can actually change these values if we wanted to be weird. So here's a little tool that lets us rewrite the values of the individual samples. One thing I didn't mention was that there are two streams of data here. There's the one on top and one on bottom. And that's because this is actually a stereo recording. There were two microphones used. This gives it stereo spatial features to the music. Notice that the two signals are similar, especially when we're zoomed out, you'd see they're similar, but they're not exactly the same. During playback, these are played to different speakers, your left and right speakers. So here, I have to zoom in to be able to actually rewrite it. Okay, there. Making my own modifications to the sound. Now, this is a very short window of time. So when I zoom out, there, you see what I've edited. It's all condensed in one little moment of time. So, of course, this short period of time, it's not going to be easy to hear. When I play it back, it's just going to sound like a little click or clap. It's not playing through the speakers as I want it to. Well, for whatever reason, this is not playing out through the room speakers. Oh, I see. There's a button underneath play here that should let me pick the output.
It's going to be really loud now, maybe. What? I can hear it here. Okay. Does anyone hear a little clapping?
I hear that little tick.
So that's
Right.
the nice sound.
That's the editing I did. So this was an example of signal processing, which is really a big part of what this class is about. Of course, what I did here was manually process the signal, and that's not an effective way to do it. What we really would like is an automated process that looks through the signal, finds the right moments in time to make changes, uses some mathematical tools to make the manipulations that we want, and also understanding what they're going to do. We also would like to analyze signals using mathematical tools, not just to manipulate them, but also just to dissect them, understand them, pattern match them. So let's talk about some examples of signals. A signal, the definition of a signal is very broad. It could really be any function or sequence of numbers. The independent axis might be time, it often is. And if it's a sequence of numbers, then think of the indices as time indices. So here's an example of just an arbitrary, an artificial signal that I created. Now, one very common thing you might want to do is smooth a signal. And you see here I have a red line going through the middle that kind of represents the smoothed version of this blue signal. So one motivation for this is maybe you're trying to measure something you expect to be smooth, but your sensor measurements jump all over the place, and you want to interpret that as noise. So aside from drawing this by hand, can you think of an automated way of smoothing? Yes, averaging. Yes, that's a great example. And how would you do averaging? Okay, so you mean not to average the whole signal, but average locally around the point that you're trying to smooth. Perfect. So this technique is going to be directly applicable to what we're talking about in this class. Now, you actually can get different effects depending on how you do the averaging. For example, you could just, for each output point, you could just go a certain number of samples or a certain length of time before that point and after that point and just take an average of your signal. And that average then would be your output at that point in time, or that time index. That's one way to do it. But you could also do a weighted average. You could count the points closer in time more heavily and the points further away in time less heavily. So in general, this sort of weighted averaging is something known as convolution, and we're going to study that in detail. And the great thing is that convolution can be understood very well through the math tools we're going to cover in this class, in particular the Fourier transform. So you'll know exactly why or what the effect will be of using one sort of weighted average versus another. Can you think of another smoothing technique that's not average, or at least not the normal mean? Okay, that is to use the median. So the local median is a way of doing smoothing that sort of removes outliers. So if you have something that's far away from your true signal, but it infrequently occurs, then it'll be removed completely from the median filter. It's a very useful filter. However, it is out of the scope of what we'll learn in this class, so there are limits to what we learn in this class. It's very, very broad, but limited. Now, this picture depicts what we would call a system, which is usually studied along with signals. if we're building a system that takes inputs from, let's say, sensors from the world and it acts on the world through actuators, and in between it does some processing, then really this is a large part of what engineering is about, is building systems like this. So we might want to know, how do we build a system to do what we want it to in terms of signal processing? Or we might also want to know, if you have a system, maybe we didn't build it, maybe it's just a room and you want to understand the echoes through a room or all sorts of physical systems, then again, you would want to be able to understand what is it going to do to a signal. So that's why systems and signals are studied together. So here's an example of a signal being image. And it's a processing that you might want to do of deblurring an image. So blurring happens when a camera is moving while an image is taken. So here's a couple examples of blurry images. And next to them are images that have been deblurred. You'd like to just do a process, a mathematical process that can recover a sharper image from a blurred image. There are tools to do this. Adobe Photoshop has tools, and they come out with new ones each year and improvements. So it's still an active area of development. And we will see some simple techniques that can at least get started in deblurring an image using just the basic mathematical tools that we learn in this class. Here we see a touch surface. And of course, this is the job of sensors to figure out where fingers are touching the surface, figure out whether there's multiple fingers, whether gestures are being made. And all of that has to go beyond just the sensors, but also the processing of the information signal coming from the sensors to detect what the intention is of the movements and to distinguish touch from just some noise in the sensors and so forth. So if you think about it, a large part of any engineering device, including a touch surface phone, for example, involves signal processing. Here next we're looking at radar and tracking. Of course, the idea of radar is that a signal is actually sent out from the radar device, some electromagnetic signal, radio waves, microwaves. They hit an object and they bounce back. And depending on the timing, depending on the Doppler frequency shift, you can infer things like direction, distance, speed of the objects that were hit. So this is a direct application of signal processing. Beyond just inferring those things that I mentioned, you also might want to track an object over time. So you'd say, well, if your radar signal said it was at a certain position and velocity at one moment in time, and another moment of time if it's in an inconsistent position and velocity, then you would use some sort of smoothing technique, which is another signal processing application to track and remove whatever noise is possible out of your radar. So the material we're learning in this class is directly applies to this type of technology. Absolutely. Now, there's a part of what we won't cover. Signals and systems in general uses a lot of probability. And we're not assuming that you've studied probability, so we're going to be learning things that do not, for the most part, do not utilize probability, which means you wouldn't be able to derive all of the best state-of-the-art techniques for tracking and radar without going into probability. Okay, beyond that, digital communication is another big application area of signals and systems. So communication technology is designed in a way to carry information that's robust to errors due to noise, interference, multipath. So here we've depicted some wireless cellular communication, some Wi-Fi, some wired networks, and all of these use signal processing and signal analysis in many ways. For wireless, you're directly designing signals to be carried by electromagnetic waves in such a way, like I said, that will be robust to noise. And one part of that is that a wireless signal can bounce off many paths to get to its destination. And this appears as a bunch of echoes in the received signal. And echo cancellation is something that's very well handled and understood through the Fourier transform, which is, I guess this is the first time I've mentioned that so far, but that's the big emphasis of this class and what you're going to become very familiar with. Another aspect of communication is sending multiple signals over the same resource. For example, the same airwaves. You can use different frequencies and channels to send multiple audio signals, for example, at the same time. And that's what happens when you do FM and AM modulation over the radio, for example, or cellular phone modulation, where many of you can use your phones at the same time from the same room. It doesn't interfere with each other because we design the signals that way. And this will be something you understand very well from the material of this course. As you can probably tell, the audio recording didn't work during this lecture. I've been dubbing over the whole thing, and it's taken me too long, so I'm not going to carefully dub over and try to repeat what I gave in the lecture, but I'll give a brief explanation with a special focus at the end when we get into complex numbers, because that's quite important. So let's see. The next application we were going to talk about was medical imaging. I actually will give a lecture later in the course after the midterm, giving applications, showing how the tools of this course are extremely relevant to medical imaging. Here I have a picture of an MRI, which is a very fun one because the Fourier transform, big topic in this course, is exactly what's used to produce MRI images. But actually other modalities, including X-ray, CT, ultrasound, also are understood through different techniques of signal processing. They're great applications, great examples. Some other examples of information signals are machine learning recommender systems, face recognition, and parts of these, like face recognition, some pre-processing would have to do with the material of this course. Other things are in the general area, but not directly related to what we'll learn here. Another information signal is the stock market. And there are a lot of attempts and some successes at predicting the stock market to some degree. And that is a great example of signal processing and using information signals and analyzing them. Here I show an example of a physical system that you can think of as processing an information signal just through physics. That information signal would be this input, which I've drawn here. A bump in the road is the height of the road is an information signal coming into the wheels of the car. And the car responds to this signal through its shock absorption system. So the suspension of the car will determine how much the car shakes up and down. Now, the process of the input, the road's height, to the output, the car movement, is a process of a system that we'd like to understand, and you can understand through many of the tools of this class. At the end, we'll talk about control systems and particular types of systems that are linear in time invariant, and car suspension, when it's idealized, is in fact linear in time invariant. So you can understand a lot about how it will behave with different inputs. And you can use that to design the suspension so that it behaves in a pleasant way, in a way that gives you good traction and is still pleasant, something like that. So again, it'll all come down to the types of math tools that we learn with the Fourier transform and the Laplace transform. Here I'm showing a circuit, which is an amplifier that does process signals. A signal comes in on the left and goes out on the right. And often it's the case that you need to design a system to perform some sort of processing task on an information signal, and you need to use circuit components to do it. Many of you probably recognize this object here. This is a Segway. It's very fun to ride. You stand on it. It's a two-wheeled object, and it controls itself automatically to stay standing vertically. You lean forward and lean back to make it move forward and back. Now, this is a great implementation of a very classical control problem. It's called the inverted pendulum problem. The inverted pendulum is a situation where you want to stack a pendulum on its end and you want to control it by moving the base. That's exactly what this Segway does. And as I mentioned before, control, in particular, making what would naturally be an unstable system stable through automated feedback control requires sound design principles, and most of those are based on these the principles we learn in this class. In particular, again, I'll mention the Laplace transform. And understanding the Laplace transform well will help you understand how to design a system that is stable. And, now, you may not think of this system as processing information, but really the physics of how it is leaning and how the person controlling it is leaning is like an input signal, and the movement of the the location of the Segway and where it moves is the output signal, and you want it to be controlled in a stable way. You don't want this thing to go oscillating back and forth or fall over because the input signal wasn't perfect. Another great control example, very much like this, is controlling a rocket or even a high-speed military aircraft. These are not naturally stable. A human would have a hard time steering them in such a way that they stay going in the direction they need to go and are safe. But automated control electronically is what allows them to fly the direction they're intending to fly. Next, let me show a quick video online that shows some nice tricks using automated control.
Meet Switchblade, a unique agile robot from the Coordinated Robotics Lab at UC San Diego. The treads provide traction over a variety of terrain, but Switchblade has another trick up its sleeve. Each tread assembly can pivot relative to the central chassis. We can use this ability to change the center of mass and climb over obstacles. Using internal sensors, we can also balance on the end of the treads and stand upright.
Okay, that was fun. Now, sound is, in fact, a great example of an information signal that we will use over and over in this class because we can work with it. It makes sense to us. We can listen to it. We will be able to open up sound objects in MATLAB. You'll do this on a regular basis in your labs, and we'll be able to manipulate them and analyze them. Now let's talk briefly about some mathematics that are a little more directly related to the content of this class. Look at the graph at the top here. This is a periodic waveform. That means it repeats. There's some obvious structure to it, right? Describing what it's composed of, describing how it behaves during each cycle, doesn't look so simple. You could say it goes up and down and blah blah blah, but it turns out that it actually has an extremely simple structure if you know how to look at it. Now, the plot beneath it shows 3 sinusoids with the appropriate scaling and shifting, meaning vertical scaling, horizontal shifting, that when you add them together, they give you that signal above. Now, knowing that gives you a very simple description of the above signal as all you have to do is specify what is the frequency of these sinusoids, how much are they shifted, and what is their vertical scaling. That's just 3 numbers per sinusoid. So 9 numbers here will tell you exactly what signal you're dealing with. So this sort of a decomposition is often very useful, and we call this a transform, a different way of looking at your information signal. Decomposing into sinusoids is exactly relevant to what we will do in this class, and that's what the Fourier transform does. What's maybe surprising is that you can do this in general, not just for this particular signal. Even for signals that aren't periodic, you can do something related to sinusoids where you construct the signal from sinusoids, and that's the magic of the Fourier transform. Now, what I have left to convince you is why that's in fact useful. But in this case, you might at least accept that it's useful because it gives us a simpler description. We have just a few numbers to describe the above signal. And having just a few numbers is referred to as sparsity. So in this viewpoint, we have a sparse description of the signal, and that's almost always useful. So here I'm showing the course website. You have access to this, I'm sure, or you know how to get access to it. It gives an outline of what we will do. It tells where the room is, where the office hours are. It also has all of the problem sets in the menu to the left, all of the assignments, including all of the labs and all the material you need to do the labs. They'll be done in MATLAB, but assuming you have access to MATLAB, then all of the material is there. And also these lecture videos, of course, are linked there. Grading policy, anything of that nature is all on this website. So please take a look. And notes as well, the notes I use while teaching, I post online and you can access them. Now I'm going to get into some actual material. We're going to learn about complex numbers. For many of you, this is a review, but it doesn't have to be. Don't be intimidated if you don't know about complex numbers. They're actually very fun, and I expect that even if you've heard of imaginary numbers, which I'm sure almost all of you have, most of you probably don't know how incredibly useful they are. And that's what I'm going to convince you in these last few minutes as well as in the next lecture. So to begin with, we have this number I, the imaginary number. Now, the imaginary number is defined to be the square root of -1. Of course, that sounds like a nice joke because we know -1 doesn't have a square root. When you square any real number, you get a positive number. Square root of 4 is 2 or -2. But the square root of -4 without complex numbers doesn't exist. Okay, so here's where we start. Define I to be the square root of -1. Now, it turns out it's much more than a joke. It actually simplifies a lot. We're going to use this because it simplifies mathematics. Okay, so then you can have a complex number is one that might have a real part and an imaginary part. These don't mix, but you can have something like 1 plus I. The real part is 1, the imaginary part is I. And combined, they're a complex number when you add them. Now, instead of a number line, you have now a plane. Complex numbers are points in a plane, whereas real numbers were points on a number line. This plane we refer to as the complex plane, and usually you plot real numbers horizontally and the imaginary part vertically. So a complex number can be thought of then as a vector. It's a two-dimensional point. It has a real part and an imaginary part. But in fact, it has much more structure than just an arbitrary vector, and that's what we're going to see. And it's actually quite nice. So the number above, 1 plus I, is plotted there in blue. And we know some simple arithmetic is just very natural. If we want to add two complex numbers, for example, we just do the obvious thing, just like adding vectors. Add the real parts, add the imaginary parts. Okay. So as we're familiar with vectors, adding complex numbers would just be like treating these 2 points in the plane as vectors and adding them up. When you add vectors, you put them end to end, and you get the new point caused by putting the two arrows end to end. Now, we would also like to understand how to multiply complex numbers. You don't have a definition for multiplying two vectors. There's not just one definition. We have things like dot products, but that's not what we're after here. We want multiplication that makes sense with what we understand multiplication to be. If you write out two complex numbers, as in the case I have right here, we know these are sums. Within the parentheses are sums, and we can multiply out binomials. So we don't need an extra rule to know how to multiply complex numbers. We can just use what we know from high school, or from, I guess, junior high, that you multiply each component of these terms in the sum. So really, no new rule was needed here. Of course, we know how to multiply a real number and an imaginary number together, because we just treat I as a variable, right? And we know that I squared is -1. And so we end up with just terms of real parts and imaginary parts. We get a new result. Now here's where the real magic is for complex numbers. What I hope you take away from this portion of the lecture is that we actually have a way to understand multiplication much nicer than this binomial multiplication. There's a much simpler way to understand how these vectors are multiplied, and this really comes from Euler's identity. Euler's identity is a result that we will exploit over and over for everything we do in this class. It's the reason we're going to use complex numbers in this class. So here's Euler's identity. E to the it for any t being real here, is cosine of t plus I sine of t. So e to the it has a real part and an imaginary part that's split up this way into a cosine and a sine. Many of you may have seen the special case where you plug in pi for t. When you plug in pi, you get e to the I pi equals -1, or e to the I pi plus 1 equals 0. Many people cite that as their favorite formula in math. How do you verify this? Well, in fact, it's very easy to verify this somewhat bizarre expression. We can verify it using Taylor series expansions. The Taylor series expansion just means match all of the derivatives. If you match all of the derivatives of a function that's sufficiently smooth, or what we call analytic, then you've exactly matched the function. You actually have equality. And all of the derivatives on the left are easy. Derivatives of exponentials are super easy. Derivatives of trigonometric functions are also easy. And you can take all the derivatives and you can verify they're equal on the left and the right there. So this formula gives us a new way to interpret a complex number in what we'll call polar coordinates. Polar coordinates, so notice that if we have a and theta being any real numbers here, we'll think of a as an amplitude and theta as a phase. Then if we write out this expression and use Euler's identity above, we can say this equals a cosine of theta plus I a sine of theta. Now, let's think about this geometrically. What does that mean? It means if we take any point in the complex plane, okay, so any complex number, we're going to get a new way to interpret that complex number. Before we were thinking of it as a real part plus an imaginary part. But in fact, we can think about it as its radius to the center of the plane, to the origin, and its angle. And this expression tells us, because of what we know about cosine of theta and sine of theta, this is exactly an expression saying that a is the radius and theta is the angle. So it was convenient that we named theta, because we usually use that for angles, right? So this, in polar coordinates, you express the complex number by its radius and its angle. And the beauty is, I mean, you could have done polar coordinates even without talking about complex number, but the beauty is that polar coordinates in this case are written simply as a e to the I theta due to Euler's identity. Okay, looks like the video's over.